Right now, somewhere in the night sky, a star is dying. But this one will not go the way you'd expect. There will be no supernova, no blinding flash, no expanding shell of fire painting the darkness for the next 1,000 years. One night the star is simply there, burning with the light of 100 suns, and by morning it is gone, as if something reached across space and quietly switched it off. The star did not drift away. It did not fade. It collapsed, straight down into a point, and in the silence it left behind, something new was born. Something that gives off no light of its own, that swallows anything that comes too close, and that will still be here long, long after the last star in the universe has burned out. We are used to thinking of dying stars as endings. But the biggest stars don't end. They transform. And the thing they leave behind may be the reason you exist at all. To understand how, we have to ask a question that sounds simple, and turns out to be one of the most unsettling in all of science. How big can a star actually get, and what happens when one gets too big to die the normal way? Let's start with something familiar. Our Sun. It is so large that you could fit around 1 million Earths inside it, and it is so heavy that its gravity holds every planet, comet, and speck of dust in the solar system on a leash, out to distances light itself takes half a day to cross. By any human measure, the Sun is a giant. And by the standards of the universe, it is completely, almost embarrassingly, average. A middleweight star. A pebble. Because stars come in a staggering range of sizes. Turn up the mass, and you get the blue giants, stars 10, 20, 50 times heavier than the Sun, burning so hot and so fast that they tear through their fuel in a few million years, a cosmic blink. Keep going, and the numbers stop feeling real. The largest single star we have ever found sits about 20,000 light-years away, and it is called Stephenson 218. If you could somehow drop it into our solar system in place of the Sun, its surface would not stop at Mercury, or Earth, or even Jupiter. It would swallow the orbit of Saturn whole. Light, the fastest thing that exists, which crosses our entire Sun in about 4.5 seconds, would need more than 9 hours just to travel once around this star. Hold that image, because here is where it gets strange. You might think we could just keep going, that somewhere out there is a star 10 times bigger, 100 times bigger, without limit. But nature slams a door shut. A star is a permanent war between two forces, gravity crushing inward, and the outward pressure of the light and heat pouring out of its core. The bigger the star, the more furiously it burns, and past a certain point that light becomes so intense that it does something violent. It starts blowing the star's own outer layers off into space, faster than gravity can hold them. The star begins to shred itself with its own brilliance. Physicists call this sealing the Eddington limit, and for the stars in the universe around us today, it means there is a rough maximum, a few hundred times the mass of the Sun, and no more. So that should be the end of the story. A tidy upper limit. Except it isn't. Because when astronomers look deep into the past, and in space, looking far away always means looking back in time, they keep finding evidence of things that, by this rule, should not be able to exist. To find out what they are, we have to follow a dying star all the way down. Every star is living on borrowed time, and how it dies is decided almost entirely by one thing. How much it weighs. A star like our Sun dies gently, almost beautifully. When it finally runs out of fuel, billions of years from now, it will swell into a bloated red giant, shrug off its outer layers in glowing rings of gas, and leave behind a small, dense, cooling ember called a white dwarf, the exposed core of the dead star, roughly the size of the Earth, that will simply fade over the ages. No violence. A quiet retirement. But make the star heavier, 8, 10, 20 times the mass of the Sun, and death arrives as the single most violent event in the entire universe. When the core of a giant star finally collapses, it does so in less than a second, and it rebounds in a titanic explosion we call a supernova, briefly outshining every other star in its galaxy combined. This is not just destruction. This is creation. The gold in the ring on someone's finger, the iron in your blood, the calcium in your bones, almost every atom heavier than iron was forged in the heart of a dying star and flung across space by a supernova. You are, quite literally, made of the ashes of stars that exploded before the sun was ever born. And when the fireworks fade, they leave a corpse behind, a neutron star, a city-sized ball so dense that a single teaspoon of it would weigh as much as a mountain. Now turn the dial higher still. For the truly massive stars, even a supernova is not enough. Gravity is so overwhelming that nothing, not the explosion, not the pressure of the neutrons, not any known force, can stop the collapse. The core keeps falling, past every limit, down to a point of infinite density, and around it space itself folds so steeply that not even light can climb back out. A black hole is born. That is the textbook. Small stars leave embers. Big stars explode and leave neutron stars. The biggest explode and leave black holes. It is clean, it is orderly, and for the very largest stars of all, it is wrong. Because some of them, it turns out, skip the explosion entirely. And in 2015, for the first time in history, astronomers caught one in the act of vanishing. In a galaxy about 22 million light-years away, there was a star. It was a supergiant, around 25 times the mass of the Sun, catalogued and unremarkable, one glowing point among billions. Astronomers had been watching it for years. Then, around 2009, it did something odd. It flared up, brightening for a few months, exactly the kind of restless behavior a massive star shows near the end of its life. Everyone expected the obvious next chapter. A supernova. A brilliant explosion. A new neutron star or black hole announced to the cosmos in a blaze of light. It never came. Instead, the star did something that had only ever existed in theory. It faded, and then it was simply gone. Astronomers pointed the Hubble Space Telescope, and later the infrared eyes of Spitzer and the James Webb Telescope, at the exact spot where it had been. Nothing. No supernova remnant, no expanding gas, no fading glow. Just a faint whisper of infrared light where a star used to be. They had witnessed something astonishing. A failed supernova. A star so massive that when its core collapsed into a black hole, the newborn black hole swallowed the explosion before it could even begin. The star didn't blow up and leave a black hole. It was eaten, from the inside, by the black hole it became, quietly, in a single gulp, leaving nothing behind but a shadow. Think about what that means. The most powerful explosions in the universe, the supernovae that seed galaxies with the stuff of planets and people, for the heaviest stars, they can just fail. And this is the crucial clue, the thread that, if you pull it, unravels one of the deepest mysteries in modern astronomy. Because if a 25 solar mass star can collapse straight into a black hole with no explosion, what happens when the star isn't 25 times the Sun, but 10,000? 100,000? What happens when the very first stars in the universe, born under conditions that will never exist again, grow into something we have no word for except monster? To find the real monsters, we have to travel back almost to the beginning, to the universe as it was just a few 100 million years after the Big Bang. It was a completely different place. There were no planets, no galaxies as we know them, no gold or iron or oxygen, none of the heavy elements yet, because none of them had been made. There was only hydrogen and helium, the two lightest gases, drifting in enormous dark clouds. And that changes everything about how stars are born. Remember the Eddington limit, the way a star's own light blows it apart and caps its size? That cap depends on those heavy elements, which catch starlight like a sail catches wind. In the early universe, with none of them around, the brakes were off. Gas could pile onto a newborn star far faster, and far longer, than anything possible today. These were the first stars ever to shine, astronomers call them population 3, and the models suggest they could have grown to hundreds, even 1,000 times the mass of the Sun, blazing blue-white and blindingly bright, living furious lives just a few million years long before dying as some of the first black holes in existence. But the first stars are only the warm-up. Because in the densest pockets of that early cosmos, something even stranger could happen. Imagine gas falling together so fast, in such quantity, that it builds not a star of 100 suns, or 1,000, but tens of thousands of solar masses, a single, coherent, glowing object larger than anything the universe would ever make again. A supermassive star. And here is the part that sounds like science fiction and is, as far as we can tell, entirely real. An object that big cannot hold itself together in the normal way. Its core collapses into a black hole almost immediately, while the rest of the star is still there, still glowing, still growing. You end up with a black hole sitting at the center of an enormous star, feeding on it from the inside, its energy holding the vast outer envelope up even as it slowly devours it. Astronomers call it a quasi-star. You might call it what it really is. A black hole wearing a star as a costume. A living, shining star with a dead, hungry heart. For decades, these black hole stars were nothing more than equations, a strange possibility scribbled in the margins of cosmology, too extreme to take entirely seriously, impossible to ever see. And then the James Webb Space Telescope opened its eye on the early universe. And what it found did not just confirm the theory. It broke the timeline. Here is the problem the textbooks had, long before Webb. The supermassive black holes we see at the center of galaxies today, millions to billions of times the mass of the Sun, are supposed to have started small and grown slowly, feeding over billions of years from ordinary stellar mass seeds, the corpses of exploded stars. That story works fine for the universe as it is now. But when Webb looked back to the first billion years, it found supermassive black holes that were already there. Already gigantic. Fully grown monsters in a universe that was barely a toddler. The math simply does not work. There was not enough time. A black hole seed a few times the mass of the Sun, even eating as fast as physics allows, cannot balloon into a billion solar mass giant that quickly. It would be like finding a fully grown adult in a room full of newborns, and being told they were all the same age. Something is wrong with the story. And then, in 2026, it got dramatically worse. Or, depending on how you look at it, dramatically more exciting. Webb measured one of these early black holes directly, and found that it outweighed every single star in its host galaxy combined. Read that again. The black hole was heavier than its entire galaxy of stars. It wasn't a monster that grew up inside a galaxy. It looked, for all the world, like it came first, like the galaxy grew around it. Around the same time, astronomers began making sense of a strange population of objects Webb had been finding by the thousands, faint crimson specks scattered across the early universe that they nicknamed the little red dots. The leading explanation is that each one is a young, hungry black hole, gorging on gas and glowing red through the dust around it. The early universe, it seems, was littered with feeding black holes, far more, far bigger, far sooner than anyone had planned for. So how do you build a billion solar mass black hole almost immediately after the Big Bang? You already know the answer, because we just met it. You do not start from the corpse of an ordinary star. You start heavy. You start from a monster, a supermassive star, a quasi-star, a black hole star that collapses straight past the explosion and hands the universe a seed thousands of times heavier than any dying sun could ever provide. The failed supernova we watched vanish, scaled up to the dawn of time. The monster stars weren't a curiosity at the edge of the story. They may have been the beginning of it. And that reframes everything. For a long time we told the history of the cosmos in a certain order. First came the stars, then the stars gathered into galaxies, then somewhere in the crowded hearts of those galaxies, black holes slowly grew. Neat. Sequential. Comforting. But the monster stars flip it around. In this new picture, some of the very first things to form were black hole seeds, the collapsed hearts of the universe's first giants, and it was these seeds, sinking to the centers of the gathering gas, that anchored the galaxies and pulled them into being. Not stars first, and black holes later. Black holes and stars, born together, in the same violent dawn, with the monsters, perhaps, leading the way. Follow that chain forward, and it runs all the way to you. A monster star is born in the dark, dies without a sound, and leaves a heavy black hole. That black hole feeds and merges and grows over billions of years into one of the true titans, something like TON 618, a black hole so vast it weighs 66 billion suns, with an edge so wide that light would take days to cross it. Around such giants, galaxies assemble. Inside those galaxies, ordinary stars are born and die in the more familiar way, seeding clouds with carbon and oxygen and iron. Those clouds collapse into new stars, and around one unremarkable, middleweight, beautifully average star, a small rocky world forms, with oceans, and eventually, with someone standing on it, looking up, trying to work out where it all came from. So come back, one last time, to that dying star from the very beginning, the one that vanished in silence, with no explosion, no farewell. We called it an ending. It was nothing of the kind. It was a seed being planted. The biggest stars in the universe do not die so much as they change costume, shedding their light and becoming the dark, patient engines that outlast every galaxy, and that may have built the galaxies in the first place. The monster was never the star. The monster is what the star becomes. And the next time you look up at a quiet, ordinary night sky, remember that the silence up there is not emptiness. Some of it is the sound of monsters, doing the slow and ancient work of building everything, including us. If this rewired the way you see the night sky even a little, stay with us, because the universe has far stranger stories left to tell, and we are only just getting started.